It's especially great to be here because I drove in this morning and I started to get worried that I didn't leave early enough, but I'm here. But then after being relieved at getting here, I realized that the one thing I forgot was my talk. It's in Chicago, but hopefully this will go okay anyhow. So it's a good thing I remembered the title. So this is a joint project with Agnes Boudry, Prasit Bhattacharya, Dominic Culver, and Jolie Zhu. Okay. Right, so what are we doing? The idea is to try to compute the TMF-based atom spectral sequence for something. And it turns out that this spectrum Z is the easiest something I can put there, where the answer is somewhat not trivial. So Z is a starting point. Turns out to be an easy spectrum for this. Okay, so let me just give you a bit of background here, like what is the deal here? Why are we doing this? So background. Mark Mahowald did extensive computations with the BO-based atom spectral sequence. A lot of these computations were joint with many other people. Don Davis, Lellman, he's done stuff with a lot of different people with the BO-based atom spectral sequence. So BO means connective K-theory spectrum, little BO. And one particularly fruitful example he studied. One example he studied was the case of a spectrum which is colloquially called Y. But that spectrum is actually the mod 2 Moore spectrum smashed the cofiber of eta. And the reason why this spectrum is there's two reasons why this spectrum is very nice. So the first thing is that if you take, is that Y, well, it's a type 2 spectrum, but if you know something about V1 periodic homotopy, you know that the mod 2 Moore spectrum only has a V1 to the 4th self-map, reflecting the 8-fold Bott periodicity. But this spectrum Y has a V1 to the 1 self-map.
So it's type 1.
Oh, sorry, type 1, yes, thank you. And the second thing about this spectrum Y is that if you take BO and smash it with Y, you end up getting connective Morava K-theory. So BO has some nastiness, but Y kind of undoes the nastiness and mods out by 2. So what is this spectrum Z? The spectrum Z was introduced by Bhattacharya and Egger. And it basically has the analogs of these two features. So the first and probably the most surprising thing about it is this turned out to be, so Bhattacharya and Egger showed that this spectrum Z has a V2 to the 1 self-map. This is the first example of a type 2 spectrum at the prime 2 that exhibited a V2 to the 1 self-map. And the second property is that if you take TMF smash Z, it's equivalent to connective Morava K-theory. And I think I don't really need to tell you anything else about Z for you to understand how I'm going to use it in this talk. Okay, so we want to understand the TMF-based atom spectral sequence. So what does the TMF atom spectral sequence look like? Well, it's some spectrum, or some spectral sequence where the E1 term is, maybe I'll decorate it like this. The E1 term is pi t of TMF smashed with itself s times, s plus 1 times, smashed with Z. And it converges to pi t minus s of Z. Now, the bad news with this spectral sequence is that TMF smash TMF. This is a problem also with BO in my whole study of the BO atom spectral sequence. The bad news is that TMF smash TMF, maybe I'll say TMF star TMF, the ring of cooperations for TMF is not flat. Over the homotopy groups of TMF. However, so what that means is that we don't have any nice description for the E2 term in terms of an X group. We have to literally start at the E1 term. So we do that. So we have to compute the E1 term. So we need to compute these homotopy groups, and we need to sort of understand the D1 differential, et cetera. So let's start by computing the E1 term. What's E1 is TMF smashed with itself s plus 1 times smash Z. Oh, but Z smashed with one of those copies of TMF gives me a connective Morava K-theory. So it's a lot easier than you might think. It's really the second Morava K-theory. So it's the second Morava K-theory of TMF smashed with itself s times. So the zero line is easy to understand. It's just the homotopy groups of connective Morava K-theory. What about s equals 1? Well, now it's K2 star of TMF. What's that? Well, one convenient way to compute connective Morava K-theory of anything is to use the classical atom spectral sequence. So as a classical atom spectral sequence, it'll go from X, by a change of rings theorem, it'll go from X, so I'm using the fact that the cohomology of connective Morava K-theory is the Steenrod algebra mod an exterior algebra on Q2. And so then by a change of rings, this will end up being X'd over an exterior algebra on Q2 of, well, now I have to put in the cohomology of TMFs smashed with itself s times. So cohomology of TMF is A mod A2. And so I have to put A mod A2 tensored with itself s times. And then this thing converges to the connective Morava K homology of TMF smashed with itself s times. Okay. But then I have to compute X over an exterior algebra on Q2 on this thing. So what's that? Well, what's A mod A2? It's F2 adjoin zeta 1 to the 8th, zeta 2 to the 4th, zeta 3 squared, zeta 4, etc., where zeta I is the conjugate of the xi's. How does Q2 act? So Q2 acts as a derivation. And so I just need to know what it does on the generators, and the formula is, you just read it off the coaction. Q2 of zeta I is zeta I minus 3 to the 8th. Okay? Now there's a very convenient thing that that helps you compute these X groups, and that's Margolis homology. So Margolis cohomology. What you do is you say, okay, Q2 squared is 0, so you take cohomology with respect to Q2. And what the effect of that is it allows you to pick up, there's basically just two modules over this exterior algebra. There's the free guy, and there's one where Q2 is acting trivially. And so you want to pick out the ones where it's acting trivially, and each one of those is going to give you a V2 tower, and then the free ones are just going to give you copies of F2 on the 0 line. Okay? So what's the Margolis cohomology of this thing? The cohomology of A mod A2 with respect to this differential Q2. Well, let's see here. The first guy that can kill anything is zeta 4. Zeta 4 is killing zeta 1 to the 8th. Then zeta 5 is killing zeta 2 to the 8th, etc. Zeta 3 to the 8th gets killed by zeta 6. But then the squares of all those classes then don't, Q2 acts trivially because it's a derivation. So what do you end up getting? You end up getting something generated by zeta 2 to the 4th. Zeta 3 squared, zeta 4 squared, etc., but modulo the 8th powers. Zeta 2 to the 8th, zeta 3 to the 8th, zeta 4 to the 8th. And if you do this for a bunch of these, you get a bunch of these. Kunis formula. So what do you get? What do you deduce? So deduce that the E1 term of this thing so it's F2 adjoin V1 tensored with this thing. Maybe I should give it a name. I'll call it B. Because A is already taken. It's the Steenrod algebra. So B tensored with itself S times. And then this thing, but that's not all. So this was picking up the Q2s that were acting. These were picking up the non-free summands of A mod A2. But then there's a bunch of free summands too, and this Margolis cohomology computation isn't picking those up. So you also have some kind of mysterious F2 vector space, which I'll call VI upper S. So this thing is an F2 vector space in Adams filtration 0. So Adams, like classical Adams filtration 0, like if I'm using the Adams spectral sequence to compute the E1 term. You could compute what this is, but it would be really annoying. Because what you have to do is you have to basically identify a basis for, there's a free summand in here as a module over an exterior algebra over Q2, and you have to compute a basis for that. And it's going to be really irregular and annoying, okay? But you could do it if you were sufficiently motivated, okay? But it's going to be also, let me point out that, okay, so this is random. It's annoying. And let me also point out that it turns out to be huge. Okay? Like it's, the size of this thing is growing at a rate that kind of roughly looks like the growth rate of the Kobar complex for the majority of the Steenrod algebra. So it's huge, okay? However, this thing is a compact little guy. This looks like a Kobar complex for some kind of nice little Hopf algebra. And so this guy is real compact. And it's completely controlled. Okay? Moreover, it turns out the D1 differential has a very nice formula. Okay? So this is not a very foreign thing. So let me just mention that there is something related to this. There's a related guy. Which is the second Morava stabilizer algebra. That should be a V2, not a V1. Okay, the second Morava stabilizer algebra. What does this thing look like? This thing looks like F2 adjoin V2 plus or minus tensor something like F2 adjoin T1, T2, etc., where these are the TIs in BP star BP modulo like T1 to the 8th, T2 to the 8th, etc., or sorry, to the 4th. And the map from BP star BP to HF2 star HF2, which is otherwise known as the dual Steenrod algebra, sends the TIs to the zeta i's. Zeta I squared, thank you. And so these TIs get related to these zeta i's. And so what you see here is this thing, this thing here, this thing here, this B ends up being a quotient of this sigma 2. So I guess maybe I chose my naming badly because the F2 is sort of sitting separately. Maybe I'll say this way. So I'm going to give this complex a name. I'm going to call this CS, okay? And then CS is a quotient of the Kobar complex for the second Morava stabilizer algebra. Well, almost. I'm going to put a sigma, a little sigma 2, to indicate that, so sigma 2 will be a variant where you do V2 and not V2 inverse. So it's a kind of connective version of the Morava stabilizer algebra. In particular, the formulas for the formulas in the Kobar complex for the Morava stabilizer algebra tell you the formulas for the D1 differential for this complex. So I've got this chunk. I completely understand it, and I know a formula for D1, and its cohomology is very closely related to the cohomology of the Morava stabilizer group. Okay? That's awesome. This guy, I can't do anything with. Okay? Yeah?
Isn't it the case that it's sigma 2, it's not you kill the 4th power of t and I, it's the 4th power of ti is equal to ti itself?
Yeah, I'm sorry? What? Yeah. This, okay, additively it looks like this. That's right, it's an associated graded, but let me not dwell upon these subtleties. Okay. So this complex here, we'll call this the, so this breaks up into two things. We'll call this the good complex, and we'll call this guy the evil complex. Now let me first focus on the good guy, and then I'll turn my attention to the evil guy. If you go back, so Mahowald, one of the things he did with the BO resolution is he proved the telescope conjecture for n equals 1 at the prime 2. And his proof was very different than Haynes-Miller's proof for odd primes. He used the BO-based atom spectral sequence. Well, first he did it with the mod 2 Moore spectrum, but it's much easier to do with this spectrum Y I mentioned. And what he does, he starts by computing the contribution to the E2 term via the contribution from the good complex. Okay? He computes that completely, and then he just bounds the evil. Okay? That's his technique. Actually, later on, there was work of Don Davis and others in the case of the BO resolutions has the same phenomenon. And so there was work of Mahowald, Lelman and Mahowald to compute the BO atom spectral sequence for many things. And still, they were frustrated by this evil complex. And Don Davis wrote a computer program to compute the cohomology of this evil complex in the case of the sphere and BO. But because it grows exponentially in size, he could only get out to the 20 stem using that computer program. We might be able to do better now because computers are more powerful than when Don Davis was doing this. But again, it grows at the rate of the Kobar complex, so it's exponential growth. You're not going to get too much farther very quickly. Okay. Anyway, let's focus on the good complex first. So let me say that. So this thing. Let me also mention this thing is V2 periodic. And this thing is like really V2 torsion. It's like V2 to the 1 torsion. Okay? Okay, it turns out there's a short exact sequence going from the evil complex to the E1 term of the TMF resolution to the good complex. And so you get a long exact sequence on E2 terms. let me call this boundary. All right, so we're going to start by trying to compute this. A related computation you can do is you could compute the V2 inverted cohomology of C. So then that's going to be the analog of computing the cohomology of, well, not the Morava stabilizer algebra, but some quotient of the Morava stabilizer algebra. Okay? And now if you invert V2, that kills all the evil guy. Okay? You don't have any evil guy. So this is the V2 inverted E1 term of the TMF resolution for Z. That turns out to be the same thing as the E1 term of the capital TMF resolution for Z. And that spectral sequence converges to the homotopy groups of the K2 localization of Z, capital K2. Okay, so this computation was actually done by Mahowald, Ravenel, and Schick, because this is closely related to their approach to the V2 analog of the telescope conjecture. So this computation was done by Mahowald, Ravenel, and Schick. And so basically the idea is that there's kind of a May spectral sequence that converges to this thing. So I'm going to write down the unlocalized version. The unlocalized version would look like F2 adjoin V2, and then tensor a polynomial algebra on generators corresponding to these guys with May names. So the May names would be H22, H31, H32, H41, H42, etc. So this May spectral sequence will converge to the cohomology of this good complex. And the differentials, as I mentioned, are just given by the formulas for the second Morava stabilizer algebra. So the differentials are read off of BP star BP formulas. And what they found the differentials are is, in some sense, you can just read these off of Ravenel's computation of the cohomology of the second Morava stabilizer algebra. But the differentials end up being, you get a differential d of, let me call it d2 of h, so d2 of hi2 equals v2 hi minus 2 1 squared, and then d2 of hi1 ends up being v2 to the 2 to the I minus 1 hi minus, hold on here, I think I'm, Doug, do I have this backwards? Thank you. Okay. There, how's that look? Good? Okay. Anyway, so these end up being the differentials. And if you invert V2, you don't really care what these powers of V2 are, because if V2 is inverted, you're just saying, oh, hi1 is killing hi minus 2, 2 squared, hi2 is killing hi minus 2, 1 squared, etc. And these might as well have been 1 for all you care about if V2 is inverted. So let me say that with V2 inverted, you can easily compute the cohomology. So sorry, this is a D2, and this is a D long, where the length depends on that value over there. And then what you find is that the cohomology of the V2 inverted cohomology of this C guy is an exterior algebra on classes H22, H31, H32, and H42. Actually, very closely related is work of Bhattacharya and Egger, and in particular Phil Egger's thesis. And it was either Prasid or Phil in the room. Oh, hey Phil, did you guys put something on the archive recently?
Yeah.
Okay, I didn't have a chance to see everything that you guys had in there, but does it include all this stuff I'm about to say? The E2 term of the K2 local spectral sequence? Let me write it down and you tell me if it's in the archive thing. Where they compute, so I'll say, so Bhattacharya Egger. So they compute the, they instead use the duality resolution, but get something similar. So there's a spectral sequence whose E2 page is this, which converges to the homotopy groups. It's basically the K2 local Adams-Novikov spectral sequence for. It's basically the Adams-Novikov spectral sequence for the K2 localization of Z, and their E2 term also takes this form.
You're missing V2.
Missing V2? Is this?
Yes, yeah, but I don't think we wrote it quite that way. We wrote it in terms of like group cohomology.
Right, you wrote it in terms of group co. So basically, they have a completely different take where they're instead using the cohomology of an open subgroup of the Morava stabilizer group, and they're doing very different things. But your answer looks like this.
Yeah.
Okay, great, excellent. Okay. Okay, now if you don't invert V2, you could still run this thing, and this will be the V2 torsion-free part of the cohomology of the good complex. But then there's going to be a bunch of V2 torsion of various unbounded length. Okay? So basically, this gives you an idea. So I'll say cohomology of C without this inverted equals, F2 adjoin V2 tends through this exterior algebra. Plus a bunch of unbounded V2 torsion. Unbounded because this exponents become arbitrarily large. But you can completely compute it all, okay? You can write down a basis. So that's the good complex. You can understand everything. But now we get to the evil complex. And if you know anything about atom spectral sequences, we're talking about a finite complex here. If I've got an atom spectral sequence converging to the homotopy groups of a finite complex, and I'm telling you I can compute the entire one part of the entire E2 term, then you have to know the other part must be really bad, because you're not supposed to compute the entire E2 term of any atom spectral sequence. That's, at least for a finite complex, that seems unusual. So how do you get this evil guy? So, cohomology of V, question mark, question mark. What you do is you run the entire thing, but instead of running the TMF spectral sequence to compute homotopy groups of Z, instead apply X to everything and run a TMF-based spectral sequence to compute X over the Steenrod algebra. So apply X to the TMF resolution for Z, and what you end up with is you end up with a spectral sequence that starts with, well, X over the Steenrod algebra of TMF smashed with itself S plus 1 times smash Z, converging to X of the Steenrod algebra F2, F2. Now this thing will also decompose into what we'll call an algebraic good complex and an algebraic evil complex. But now, the fundamental thing here is that remember the evil complex was concentrated in Adams filtration 0. It turns out just from that, you know that the algebraic evil complex is actually isomorphic to the topological evil complex. These are the same complexes. They're the same, together with their D1 differential and everything, okay? So the cohomologies are the same. So it doesn't matter what the evil complex is. All we care about is what its cohomology is. Now, if I can compute the cohomology, well, let me talk about the cohomology of the algebraic guy. There's also a May spectral sequence computing the cohomology of the. So there's a May spectral sequence that looks the same. F2 adjoin V2, tensor polynomial, H22, H31, H32, H42, or what am I doing? H41, H42, etc., converging to the cohomology of this guy. Basically, though, you're only running the differentials that preserve Adams filtration. And these are changing Adams filtration by, you want to run the differentials that change Adams filtration by 1. And these guys are changing Adams filtration by large amounts. So it turns out this spectral sequence collapses. So this literally is the cohomology of the algebraic good complex. Yes? Apply X? Sure. It means this. So how does the regular resolution look? It's like this. So let TMF bar be the fiber of the unit. Right? That's the regular Adams resolution. Apply X to this diagram. And you'll have like a decreasing tower of X of Z that will, oh, sorry, I said X of F2, F2. I also have a typo here. That should have been homology of Z. Was that the, okay. Sorry about that. Yeah. Okay. All right. So basically, what do we have? We have something that starts with, well, the E2 term of the algebraic TMF resolution for Z sits in a long exact sequence involving the cohomology of this evil complex and the cohomology of this algebraic good complex which I just told you what it is because the spectral sequence collapses. So in fact, this is not converges, this is equals, okay? And then this thing is converging to something else. The Adams E2 term for Z. Now, the idea is that if you know this and you know this, then you can get this. Okay? Well, we know this, and we can use a computer to know this. Computers know this. And so then we can deduce this.
Well, computers can't know all of it.
No, they can't know all of it. So you're only going to get this through a range, and the range will be dependent upon your computer and your ability to understand the spectral sequence and the connecting homomorphisms through that range. Okay? But this beats the, you see, a computer can compute this with a minimal resolution, whereas this V was like growing, it was such tremendous speed that it was getting unmanageable quickly. So this is much more computable than this. And so it's kind of a trick to get at this without having to even think about it. Okay, and then once you have this, then you feed it into the topological situation. So this is a really bizarre setup. We did this for the BO atom spectral sequence, and now we're doing it for this spectral sequence. We call this the Agatha-cockological technique because that's the only word we could find that means combine good and evil. Okay. So you do this, get this, deduce this, then feed it into here, you know this, and then start computing to get this. Okay? It's a way to go. All right? All right, so let me show you some charts. Okay, so what I've written here, this is the algebraic TMF resolution, and this is the topological TMF resolution. Okay? Now, so let me tell you how to read this picture. It looks like it's cut off slightly, but honestly, there's so many dots, it probably doesn't matter. Okay, so what are we looking at here? The black dots, so basically I took Bob Bruner's X program, ran it on this Z guy, and then drew over it, okay? So the black dots are the classes in X of the Steenrod algebra, okay? We're going up through about the 45 stem. Ooh, this is kind of bad because I want to tell you something that's happening over here. I'm not going to worry about it too much. I could trick it. Huh? Oh,
you're on, or are you on that computer?
I'm on this computer. It's okay. We'll be fine. Okay. Anyway, right. So all the black dots are classes in X of the Steenrod algebra. And then what I've done is I've drawn in V2 multiplication. So remember, there's a V2 to the one self map. So V2 actually acts on the whole spectral sequence, okay? So the blue lines are the action of the V2 self map, okay? And then the blue guys, so there are some classes in the good complex that you don't see in the cohomology of the Steenrod algebra. So every blue guy and every black dot that doesn't have a circle over it, those are good guys. Every red circle is an evil guy, okay? And the reason that there are some classes that don't correspond to X classes is because they support differentials in the algebraic TMF resolution. But what you do is you deduce the existence of these evil guys and these differentials by the lack of the appearance of these good guys in X. Okay? So, here's H22, H31, H22, H31, H31 squared. Those are all names of classes in the cohomology of the good complex over here. And so I've just labeled them on here, okay? And then I've circled all these evil classes. You're basically evil if and only if you're V2 torsion over here, and you're good if you're V2 periodic. So then you've got these. So basically, the takeaway is I've computed all the evil by locating all the good and accounting for what's left over. Okay, and then what you do is you go back and you reinsert the evil. So now what I've drawn is this is the TMF resolution for pi star z. So I started with the cohomology of C, which I mentioned is just, well, it's this exterior algebra plus some torsion, but it roughly looks like everything through this short range. So, you have like H22, H31, H22, H31, H31 squared, H32, they all have these towers on them, right? Then I've basically taken every red circle from the previous slide and just put it in its appropriate place over here, and that's the evil complex, okay? The cohomology of the evil complex. And then you do have to compute some differentials, and honestly, many of these differentials are computed by comparing what's going on with the classical atom spectral sequence and what's going on with the TMF resolution. So you kind of play one off the other here. Let me highlight something in particular. Well, it looks like I don't have time, so let me not highlight the something. Let me just say a punchline. So anyway, right. Now, as I mentioned in the, so this picture is literally lifted from Phil Egger's thesis. So hopefully this is proper attribution. So this is the E2 term of that spectral sequence. I want to point out, it turns out that there are some possible differentials in this spectral sequence, and you have no way of knowing whether these differentials happen or don't happen. But really, it all hinges on knowing if this class, you do know can't support a differential because topologically it would be the inclusion of the bottom cell into Z. It has to be a permanent cycle. But this one you really don't know, and its name over here is H32. So then you go back to the TMF atom spectral sequence, the unlocalized spectral sequence. And you see, here's H32 supporting a D1. That's really the boundary homomorphism in that long exact sequence. Then V2 H32 supports a D2. V2 squared H32 supports a D3. And here's V2 cubed H32. Well, because V2 is actually a self-map, it would have to support it would have to support a D3 differential or higher, and there is nothing to be a target of that differential. So you deduce that that thing's a permanent cycle. Well, because some V2 multiple is then a permanent cycle, that tells you then, wow, that is a strong cutoff on the talk. That tells you then that this thing is a permanent cycle. I already told you this thing has to be a permanent cycle. So turns out that there are no differentials in the spectral sequence. The thing collapses. And so this exterior algebra is actually just the homotopy groups of the K2 localization of Z. And this represents, I think, the first example of the computation of the K2 local homotopy of any finite complex that I know of. Anyway, I'll end the talk here.